Okay, so we're now dealing with chapter 2, which deals with Newton's second law. This whole topic is dealing with motion, right? Do you notice that as I walk about, I'm moving, right? And I notice that, are you moving or not? You are? When you nod your head or otherwise?
Your eyes falling.
Okay. If I were to just stand here stationary, are you moving?
Well, yeah, because your heart's beating.
Okay.
You're breathing.
You're breathing? Okay. Yes. Extra credit to you for speaking up. Ellie, right? Eleanor. Do you go by Eleanor or the shortened version? Ellie? Okay. What's your name? Ashley. Okay. Ashley, Ellie. I'll probably over time remember the names of those of you who speak up. So if you don't want me to... Okay, I have to give you incentive to speak up. Okay, so... my center of mass, and we'll see that later in one of these lectures, is like roughly about where my solar plexus is, ballpark, right? That's my body behaves as if my mass is centered somewhere there. So when I walk about, my center of mass is moving from one place to another. There's a displacement, right? Now your center of mass is typically, while you're in the lecture, is stationary. So to a first approximation, your center of mass is not moving, even though parts of you may move, right? Like your eyeballs and so on. Now, introducing a few concepts. Inertia, we've probably all heard the term. Has anybody in this room not heard the term inertia? Okay, so inertia is the property of things to resist changes in motion. It's kind of like, whatever, you need to wake up at 5 in the morning to head for your work shift, and like, you have no desire to get out of bed, right? You just want to pull the covers over your head, stay in bed till 10 a.m. or whatever. That is inertia, your tendency to stay sleeping when you were sleeping. Or if you find something totally exciting to be doing, like you're reading a totally fascinating book, or you're watching a completely fascinating movie or whatever, then like it's midnight and you're still up, right? Totally all excited in the action, and you have no desire to go to bed, even though you know you have to wake up at 4 in the morning the next morning to go to work, right? Or 5 or 6, for those of you who are slackers, right? Totally kidding. I normally wake up at as late as I can possibly wake up, which can be 8:30. Okay, so resisting changes in motion. So the fact that you are all stationary in your chairs is because of inertia. Your body is resisting a change in motion. So you're staying stationary because you started off being stationary, right? Now you will stay stationary. You'll resist a change in motion. You'll stay stationary until a force is applied on you, right? If Ellie, don't do this experiment, but if Ellie were to put her shoulder, what's your name? Jessica. Okay. If you were to, I'm not asking you to do so, but if you were to put your hand on her shoulder and push, you're applying a force on her. And what happens to Jessica, to her center of mass?
Rolls.
Yep. She will move away, right? Because of the force. So what happens is, in the absence of the force, notice that Jessica is not moving, she's stationary. But once you apply a force, she then responds to the force and moves away, right? So that's an illustration of inertia. Okay. So this is from your textbook, and this is just making the point that if you think of Aristotle versus Galileo, Aristotle believed and taught that speed of an object, when you drop an object, the speed of the object is a little tilde sign is proportional to the weight. So intuitively we know what weight is, right? Heavier object versus a lighter object. So Aristotle came along and said, if I were to drop a heavier object from, in this case, the local Pizza Hut, what happens is the object falls at a rate that's greater than a lighter object, according to Aristotle. Later on, along comes Galileo and says, no, speed is not proportional to weight. Speed of these two objects, right, when you drop them from the same height, they will both accelerate at the same rate. So the speeds are the same, according to Galileo. In real life, what do you find to be the case? Do you think Aristotle is right or Galileo? Why do you... I hear a few murmurs of Galileo. Why do you believe Galileo is correct? Why not Aristotle? I can do an experiment right in front of you to show you that Galileo is wrong. You want me to do the experiment? Okay, which of these two objects, this is the lighter object, this is the heavier object, which is going to reach the ground first? So you're saying that the speed is proportional to the weight, right? According to Galileo, they should both drop at the same speed. But in real life, let's do the experiment. Maybe, okay, what we just did is a hypothesis. We set up the hypothesis, right? Here's the hypothesis that they will both fall at the same rate, right? We said Galileo is true, so we're setting that up as, and we're going to do the experiment. So give me a prediction. This is the scientific method, right? Allegedly. Okay, this is the scientific method. Give me you told me that the lighter object is going to hit the floor first, right? The heavier object. So the object in my left hand, correct?
Yes.
So the object in my left hand is going to hit the ground. No?
Right hand.
Okay, so the object...
Metal rod.
Okay, so the metal rod is going to hit the ground first, right?
Yes.
Let's see. Okay, see? Do you see? Notice that the paper hit the ground first? Did you guys notice that the paper hit the ground first?
No.
Okay, step number 2 in the scientific method is you need to be awake when the experiment is in process. So what did we say? What did we find? Which hit the ground first? The heavier object, right? So this experiment should prove to us that Aristotle was correct, not Galileo, right?
Don't we have to account for wind resistance?
Good job, right? So extra credit to you. So the confounding factor. There are lots of confounding factors in scientific experiments. The majority of the times, experiments do not give us the results we expect. That's just real life, right? That's why it takes so long to get a PhD. I mean, literally, I've had students who work for 3 years to get the equipment to work. Then once it works, they generate a whole bunch of data in like 3 months. Then crunch the data to get their PhD, right? But it may take 3 or 4 years just to get the experiment to work. It just wouldn't work to begin with. So that's because of confounding factors. In this case, the air, the resistance to the air is a confounding factor. Now, if I were to ask you all to hold your breath and we evacuate this room so there's no air, right? But you need... Why is it that you cannot hear me?
Because sound travels a lot.
Yes, because there's no air in the room, right? We just evacuated it. And you're holding your breath. So how come you're speaking? Okay, so if we were to do this experiment now, with the room evacuated, which of these is going to hit the ground first?
They fall at the same time.
They both fall at the same speed, right? Now this is counterintuitive to those of you who don't know physics already, right? Some level of physics. However, Aristotle, for generations, people thought that Aristotle was right until Galileo came along, and intuitively, somehow, Galileo was a genius of sorts. Came up and said, no, the speed is not proportional to the rate, to the weight. They'll fall at the same rate. And the confounding factor is the air resistance, right? As you mentioned. Okay, now Galileo came up with this experiment where, in order to decrease the acceleration, the rate at which the object is speeding towards the ground, he came up with these inclined planes. That is, if we had a table that's completely flat and we put a ball, whatever, a ball bearing on the surface of the table, what happens is it'll just sit there and do nothing, right? It's not going to be moving. However, if we were to tilt the table like this, what happens is the ball bearing starts accelerating downwards. Now the rate at which it moves downwards is a certain rate. If we were to tilt the table even further, the rate at which it accelerates is going to be higher. So it'll accelerate even faster. If you take it totally vertical, then the ball bearing will fall at the same rate as if there were no table at all. So in between this, you can slow down the acceleration due to gravity, right? The rate at which the object is speeding up in order to study how the acceleration and the speeds behave. So inertia, we said, was the tendency of the object to keep moving in a straight line, or to not start moving by itself if it were stationary. So here is an example of a tub of sorts. Here's a ball placed at the top here, and we will release it. It will accelerate down this sloped surface, travel along the horizontal surface, and accelerate up to a final position in the absence of friction. If there's no friction, this height will be the same as this height. If we were to make this slope, this is a higher slope and that's a lower slope, you will find that this ball will travel a greater distance along the lower slope until its final height is the same. It's not that it would travel the same distance. So if you look at the distance from here to here, it's shorter than the distance from here to here. So if we thought it's purely a function of distance, we might say that the ball will travel down here, along here, and then up to the same distance and then come back down. That would be a hypothesis, but that hypothesis would be incorrect. In the absence of friction, it travels up until this height above the earth is the same as this height. Now if we were to lower this all the way to make it horizontal, where would you think is the final position of the ball? Absent.
If there was no friction?
If there's no friction,
It would stop.
it would never stop. Would it reach infinity?
No,
Why not?
because infinity is continuing forever. You can't reach it because it's still going.
Yes, good point. You're right, extra credit to those of you who spoke up. So the object would potentially tend towards infinity but never reach there. It is impossible to achieve a actual infinity in real life anywhere in the universe. That's an impossibility, right? That has some interesting philosophical consequences, which maybe I might comment upon at a later time. Okay, so what happens is here, due to inertia, the object will just keep on traveling. Now in real life, if I were to roll a ball along the floor, after a while it comes to a stop. And the reason why it comes to a stop is because of friction. What happens is the surface of the ball is interacting with the surface that it's rolling upon, and there are bonds that are made and broken, typically like hydrogen bonds, van der Waals bonds, or maybe electrostatic attraction, that kind of stuff, that uses up some of the energy, and the ball will ultimately come to a stop, right? But that's because of friction. If there were no friction, this would keep going on forever, in principle. Okay, Newton's first law. Now, inertia is Newton's first law, right? Which basically says that the object continues at rest if it started off at rest. If it was stationary, it will stay stationary. Due to inertia, Newton's first law, it will continue in a straight line if it were moving in a straight line to begin with, if there's no force applied on the object at this given time. So example of inertia, you've probably all done this, right? Like you're nailing, using a hammer to nail nails, and what happens is the head of the hammer becomes loose. What do? Do you turn the hammer on its head and hit the head against the table to get the hammer to tighten up? Or do you do it the inverse? The inverse, right? So what we do is we hold the hammer like this and we bring it down hard on a hard surface. So we're doing this to the handle of the hammer, and what happens is, due to inertia, once you've accelerated the whole thing, when you hit the base here, the table or the floor or whatever, you're suddenly bringing this handle to a stop. What happens is the head doesn't quite realize that the handle has come to a stop, so it'll keep going due to inertia. So as it keeps going, it jams itself tighter onto the handle, right? And the handles are typically, they have a tapered, often they're wood, and the wood is tapered at the end, and the head also has a tapered opening, so it jams in and it travels as deep as it can until the taper stops it. Okay, that was an application of inertia. Okay, we talked about an illustration with Ellie and Jessica. Okay, my apologies in advance if I forget your names, right? If it does, then I apologize and I'll get the correct name again, I hope. Unless you say that your name is Tim, then I'll be highly confused.
We get it, Paul.
Oh, Paul. Good, I love it. Extra credit to you. So that's just a reminder that if I forget your name, then you can take revenge on me by forgetting my name, right? Cool. Okay, a force. We talked about, right? If you were to apply a force on your neighbor, a push on your neighbor, the neighbor begins to move. So in the simplest sense, a force is a push or a pull. So introducing the concept of a net force. So here is an object, a block of wood. There are two forces applied on it, a 5 Newton force pulling to the right and a second 5 Newton force pulling to the right. This is the applied force. This is equivalent to the object with a net force where you add up these two. So Newton, the term N, the little n or the big N, is referring to the units of force. Force are measured in newtons, right, in this course. 5 newtons plus 5 newtons both to the right, this is the net force, 10 newtons to the right. Now if I had 5 newtons pulling in this direction, 5 newtons pulling in the other direction, so in this example, let's say we're not going to do this experiment because we don't want to hurt Ellie because we like her, right? So let's say that Jessica, we're going to grab Ellie's arm and pull her to your left. And what's your name?
Yvonne.
Yvonne. And Yvonne is going to grab Jessica's other arm and pull her to your right. Did I say Jessica's?
Yes,
Thank you for catching that. Yes, you're right. That would be hard to pull Jessica's arm because she's like way over there. So you want to be pulling Ellie's arm, right? So Ellie's being pulled in two different directions. Now let's say that both of you were on one side. You apply 5 newtons, you apply 5 newtons. Now Ellie will come accelerating towards you as if there's a 10 newton force on her. However, if you apply 5 newtons in this direction and you apply 5 newtons in this direction, they two effectively cancel and Ellie stays stationary, right? And just puts her feet up on the floor, on the table, and smokes a cigar, happy as a clam, right? Nothing in favor of cigars, but okay. Not speaking in favor of them. Okay, so that's this situation. So the effective force is 0 newtons. Now if you had 10 newtons to one side and 5 newtons to the other, the net force becomes the 10 minus the 5. So 10 minus 5 is 5. So this body behaves as if there are just 5 newtons pulling on it, in this case to the right. So the force, the net force, is the net push or pull on the object. Introducing the concept of the equilibrium rule. The equilibrium rule basically says that the net force is 0, and that's why you're stationary. If you are in equilibrium, you will not accelerate in any particular direction. Each of you is stationary right now. How many forces do you think are applied on you at this instant? Okay, one is gravity. Say anything else? Okay, so far our combined wisdom tells us that there is one force applied on each of you, right? If there is one force applied on each of you, and it's not 0, right? It's a non-zero force, you must be accelerating towards the center of the earth. Correct? Because if you're being pulled towards the earth, if that force is not counteracted in some way, you must accelerate towards the center of the earth. Why is it that you're not accelerating towards the center of the earth? Good job. Extra credit, right? Who spoke? Perfect. Heard a voice. So, right, the chair is pushing up. That's called a normal force. The chair is applying an upward force on you where you are in contact with the chair. And that upward force exactly counteracts the downward force of the earth. What happens if the upward force due to the chair were greater than the downward force due to gravity? What would happen?
Float.
Yep, you would actually flip up into the air like popcorn, right? Because the force would be greater, you'd accelerate upwards. It's not that you'd float and be stationary, you'll just start accelerating upwards, right? So you'd watch your head with the ceiling tiles. It's amazing that we live in a universe where these laws work. It really is totally amazing. We take it for granted, but it really is amazing that physical laws work and they behave in such a rational, uniform kind of a fashion. Because think of this. If gravity were to change at random, right? And you never know what's going to happen. All of a sudden the normal force is greater, you're going to bump your head against, right? You'd have to, you live your entire life with helmets and you wouldn't be able to live a rational life if we didn't have rational laws in the universe. Really weird. Again, that's another philosophical question. Why does the universe have order? Why does the universe have rational laws? And why does the universe have laws that we can understand as rational thinking beings? Right?
Is there a theory that there is no order? It's all... I can't remember the name of it. But
oh, you're talking about chaos? Chaos theory? That's the closest that I can think of. Chaos theory applies in a small frame. I mean, if you think of everything in this classroom, there's a huge amount of order in this classroom. And it's evident when we look at the fact that the students are sitting in rows and columns. That's an example of order, right? Now, chaos can apply in small sections, if you will, of the universe, small sections of physics. We can talk more about that, right? Okay, so here is a scales, right? So hanging scales, sugar attached to the hook. You pull the scale up, or rather you have it, in this case, suspended from the ceiling, and the sugar pulls this, it extends the spring, and this little marker comes down and says 2 pounds is the weight, if you will, of the sugar, which is really the mass, or 9 newtons. What happens is once this system is stationary, this hook is in equilibrium. The upward force due to the spring is equal to the downward force due to the sugar. The downward force is due to the weight of the sugar, which is arising because the earth is pulling down on the sugar. That's the downward force. The upward force is because there is a spring in here that once you extend it, it wants to get unextended, right? So it's pulling in the opposite direction, exactly cancelling this. So the equilibrium rule says basically that if this hook, for instance, is going to be in equilibrium, the sum of all the forces on it, net force, should be equal to 0. So the sum of all the forces, the vertical force minus the downward force, should be equal to 0. If otherwise, this will not be in equilibrium. So just as a reminder as well that all of these slides are on the website. So you're welcome. I think they're also in notes format. So you can print them out as notes if you want, and then write notes in class on them if you will. Okay, so mechanical equilibrium is the state of an object where there are no changes in motion. So the net force is equal to 0, and that's called mechanical equilibrium. And the equilibrium rule is basically that the summation of all the forces on the object is equal to 0. This letter here is sigma, which just means it's the Greek for capital S, S for sum. So summation of all the forces is equal to 0. That's all. Notice that these definitions have a whole bunch of text, right? Lots of words. If you just boil it down, what's the bottom line? The bottom line is that the equilibrium rule states summation of the forces is equal to 0. That's it. And mechanical equilibrium is basically the same thing, applied to like a mechanical system in terms of motion or not motion. Okay, so here's an illustration of this. A couple of painters on one of these, there's a long, whatever, plank of wood that's suspended by ropes up there. So there's an upward force on this rope, there's an upward force on this rope. Here's painter number 1, his weight pulling downwards. This is the weight of the plank of wood. Here is the weight of the second painter. If you add up all these downward pointing forces, they give you a certain force downwards. That's the force that's trying to pull the plank downwards. If you add up all the vertical upward forces, that's the force upward on the object trying to pull it upwards. These upward forces should be equal to the sum of the downward forces. So you add up all the upward forces, that's the net upward force. Add up all the downward forces, that's the net downward force. The upward force, the net, should be equal to the net downward force. And that means the summation of all the forces is equal to 0, and the system is in equilibrium. So we talked about the fact that you are not accelerating in any particular direction. Gravity is pulling you down, but what happens is there's a normal force on you. That normal force can also be called a support force. So here's an illustration where there's a textbook on the table. There's an upward force, the support force on this textbook. There's the weight downwards. The textbook is stationary, which means that the sum of the two of these should be equal to 0, right? This is the vector sum, that is including the signs. Or the magnitude. If you look at just the number, if this is 10, let's say this is 10 newtons downwards, the upward force must be equal to 10 newtons upwards, right? And this is an illustration with a person pushing down on a spring. The downward force of and let's say the spring is now in equilibrium, it's not compressing anymore, right? It's compressed and come to a stop. What happens is the downward force is equal to the upward force on the hand by the spring. Okay, same thing. Let's say in the morning you decide that you're going to weigh yourself, and here's you on the bathroom scales, and what happens is here's your weight pushing downwards on the scales, and the scales is providing an upward support force. The scales are actually measuring the upward support force that the scales are having to provide to keep you from going through the floor. So the scales are really not measuring the weight, they're measuring the support force, the force that they are having to apply on you. But it turns out in equilibrium these two are the same, and that's how you're able to read your weight. Now also colloquially, what you typically read, we read our weight in pounds, right? For whatever it's worth, pounds colloquially we think of it as weight, but really in physics terms pounds are mass, they are not weight. Weight is a force, mass is the amount of matter in the object, right? And we'll talk more about that as we go into the future. Now a moving object can be in equilibrium as well. So here's an illustration of a crate, and here's a woman who's pushing the crate at a certain speed. So the crate is moving on the floor, right, at a certain speed. She's applying 75 newtons, that's the applied force. Friction between the crate and the floor is in the opposite direction at 75 newtons. So the net force is, what's the net force? 0. So since the net force is 0, that means that the crate cannot be moving, correct? Let me rephrase that question. Let me first give you a hint. The hint is, if I ask you a question And then as I say, let me rephrase the question, and you notice that I give you exactly the same question and not rephrased. That means that I'm looking for a different answer. So let me rephrase the question. The net force is 0. That's correct. Since this 0 net force, that means necessarily that this crate cannot be moving. Correct? Good job. So, you're right that the answer to my question is no. The object could be moving. If the object was already moving to begin with, for whatever reason, it happened to be moving at a certain rate, and now if she were not applying a force on this object, friction would slow the object down until it comes to a stop. However, let's say that she decides she's going to help the object. She comes up and she pushes the object with just enough force to overcome friction, but not to accelerate the object any further. The object will just keep moving, right? So the force that she applies, all that it's doing is it's exactly cancelling out the friction force, and the object just keeps moving at the rate that it was moving before she applied this force. Right? So at the speed at which it was moving before she applied this force, this object is called being in equilibrium. It's in equilibrium because there's no net force. Notice that there's no net force. So anytime an object has no net force on it, the object is in linear equilibrium. In a later lecture we'll talk about rotation. Rotation will include torques and so on, right? But in the absence of torques, what happens is, if the net force on the object is 0, the object is necessarily in equilibrium, and the object could be stationary or it could be moving at a constant speed. Okay? Okay, so this is making the point that you're probably aware that the Earth is moving, right? The Earth is spinning on its axis, right? The Earth is spinning on its axis, and it's also traveling around the Sun. Now the Sun, the solar system, is traveling around the center of the galaxy, right? The Milky Way is whatever, 100,000 something light years across, and so what happens is ballpark of about 50,000 light years from us is the center of the galaxy, and we are all traveling like at a pretty decent pace around the center of the galaxy, right? Now the Milky Way galaxy as a whole is traveling with respect to the universe as a whole. So it's traveling probably towards the great attractor. I mean, there are gravitational centers at different places in the universe that attract the different galaxies and so on, right? So if you add up all of these different motions, it looks like the Earth is moving at 30 kilometers per second. So you are traveling at the rate 30 kilometers per second is ballpark of 20 miles per second. By the time I say 1 Mississippi, you have traveled the distance from here to downtown Phoenix. Isn't that amazing? And it's amazing that you can do that without losing your balance, without getting all giddy and dizzy, right? And confused. So that is truly amazing that by the time you say 1 Mississippi, you have traveled the distance between here and downtown Phoenix based on what the Earth itself is doing. Now, this is asking the question, the Earth is traveling at 30 kilometers per second, which means this earthworm is traveling at 30 kilometers per second. So how is it a bird cannot travel at 30 kilometers per second? No bird can fly that fast. So how is it that the bird is able to catch the worm?
So are you moving at 30 kilometers per second?
The earthworm is, because it's on the Earth. So is the bird? Okay. So it looks like 3 of you are awake. Excellent, right? So the whole slide is illustrating the concept of relative motion, right? With respect at the bird sitting there and looking at the worm, with respect to the worm, the bird is stationary. With respect to the Earth, the bird and the earthworm are both stationary. However, with respect to, let's say, the center of our solar system, the worm is traveling at 30 kilometers per hour, and then so is the bird. And so, because it's all relative in that sense, the motion, the bird is able to do this. Now, another illustration of this is if you happen to be, how fast would you say a plane flies? Good job. Extra credit to you. So, let's say you're traveling like in between cities, right? 727, 707, 747, whatever. And typically once they get into cruising altitude, they're traveling at about 500 kilometers per 500 miles per hour or kilometers per hour? I forget. Miles per hour. Okay, so it's like 700 kilometers per hour, right? So 500 miles per hour. which is pretty fast, right? So 500 miles per hour, and what happens is you toss a coin straight up into the air, right? You're tossing it straight up. By the time the coin makes it up there and comes back down, you've already traveled, whatever, 20, 30 feet in the plane. So the obvious question, which you've already answered, is why is it that the coin comes back to you? To you, it looks as if the coin is going straight up and coming down. However, to a person outside of the plane, the coin is not going up and down. What is it doing? It's traveling in a, what's the name of that curve?
Arc.
An arc, okay. A more mathematical term for it? Parabola, you're right. So it's traveling in a parabola, right? Because there's the horizontal. So as far as the coin is concerned, when it's in your hand, you're both traveling at the same speed. And when it leaves your hand, the coin has two components. The component that you gave it vertically, as well as the horizontal component that the plane gave it, just as the plane gave you the horizontal component, right? Can you think of a situation where you were to do this experiment in a moving vehicle? Like if you were to do this in a car, would it work? The coin would come back to you? Yes?
Yes. The roof was off or something, and then you have that.
Yeah, so the next question is, in what situation if you were to do this in your car would the coin not come back to you? Can you just answer the question? If you were in a convertible, right? Convertible, or you have your moonroof or sunroof or whatever open, and you toss it up, and then what happens is it goes up and poof, where did it go, right? So if you want to do that experiment, my recommendation is do it with 1 ounce gold coins, and let me know when you're going to do it, and I'll drive along behind you. All right?
So,
Yes, sir.
If we got rid of the force applied to us, and essentially we were just floating above the Earth, that means we would essentially, we'd be watching the Earth travel 30 kilometers per second beneath us.
Yes, if all of a sudden we were to completely, of course we'd have to be standing like maybe pop up into the atmosphere somewhere, then all of a sudden stop all the motion / velocity of us, and we come to an absolute stop with respect to the universe as a whole. Come to a stop, the Earth would just whiz past, right? And it would be traveling away from us at about 30 kilometers per second, right? Good question. Extra credit to you. Okay, let's look at, so just as a reminder, right? After each of these lectures, there are multiple choice questions for you guys to look over, right? That will illustrate some of the things that we're talking about, and at the end of the multiple choice questions, there are answers as well. At the very end of those. So, a lot of this understanding you would gain by the time you read through your textbook. Remember that you're supposed to read your textbook and come up with the question and answers, right? Understanding the concepts. So between the lectures and the labs and the reading of your textbook, you will have enough of an understanding to be able to answer these questions. My recommendation is go ahead, look through these questions, look through all the multiple choice questions that I provided on the website, right? By chapter, look them over, have a look at them, and go ahead and answer them. Go ahead and answer them, check the answer keys, and if there's any particular answer that you find that you don't get or that you disagree with, check with other students. My recommendation is, at least in your lab groups, exchange emails, email addresses or phone numbers, or you can catch each other before the lab or after the lab, right? Or during the lab too, and ask each other these questions. And the more you do this kind of stuff, the more you're likely to understand the concepts and do well in the class, right? So let's look at a couple of questions just as an illustration. An object freely falls downward. What do you think is the answer? Okay, there are 2 for C. Okay, 3 for C. Okay, let's see a show of hands. How many for A? Now, in general, you're supposed to pick the best answer, right? How many for A? 1, 2 for A. 3, 4. 4 for A. How many for B? Show of hands. A, what did we say? 4. B was 0. C, show of hands. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14, 15. Okay, 5. Okay. How about D? 1 for D. Okay, since we live in a democracy, we all know that once the majority votes, that's the rule of the land, right?
Right, you know.
If we were to run, should we run physics like that by majority vote?
No.
No? Okay, so going purely on a democratic basis, C would have to be the answer, right? You all cool with that? Okay, let's move on to question 2. You seem to have a problem with the methodology.
I don't agree with
Oh, you don't agree with the methodology or with the answer?
the answer.
Oh, you do not agree with the answer. Where had you voted? Oh, you had voted with A, right? Okay, so let's look at this. As the object is dropping freely downwards, it's true its velocity increases, right? Because there's a continuing force on it, right? Its velocity increases. Now, this is interesting. This is one of those questions where it depends on what level you're going to answer the question. At a level of, like a completely introductory level of physics, at the level of this lecture, the simplest answer is to say A. If the velocity is increasing, the acceleration is a constant to a first approximation, right? Now the truth of the matter is, the force due to gravity is proportional to 1 over the distance squared between the object and the center of the earth. So as the object gets closer and closer, the force will increase. If the force increases, the acceleration will also increase. So B is also correct. So at a completely introductory level, the answer is A. At one level deeper than the introductory level, the answer would be C, both of these, right? So if I were to give you a question like this, right, I'll try to avoid doing something like that. But if I were to, if you have a reasonable, I mean, I understand how some of you could interpret it one way, some of you, you're answering it at 2 different levels. So I would give both of the answers as correct, right?
What about acceleration have to deal with the direction that it's traveling? But if it's traveling downward, where's the difference in direction?
Okay. Acceleration is the rate at which the object's speed is increasing for each second. So let's say that the object, let's say that at time equals 0, let's say at time equals 0, the object is, here's its speed, right? Or its velocity. Let's say it's 0. At t equals 1, let's say that the speed is 10 units, 10 meters per second. At t equals 2, the speed is 20 meters per second. This is object number 1. Object number 2 starts out at 0. At t equals 1, it's 20 meters per second. At t equals 2, it's now 14 meters per second, right? Which is traveling faster at this moment? The object on the right, object number 2. Which of these has a greater acceleration? The one on the right. So notice that this has a certain acceleration, right? So mathematically speaking, the acceleration, okay, velocity equals the change in position over time. Delta x, change in position over time. You need to understand the concept rather than the math of this, right? So the distance traveled divided by the time gives me the velocity, really the speed. The acceleration would be the change in velocity divided by the change in time. So notice that between t equals 0 and t equals 2, in this case, the delta v for this case, delta v is 20 minus 0, it's just 20. Delta v for this case is 40 minus 0, 40. The time divided by the time delta is how much? 2 seconds, and that's the same in both cases, right? So you can see that this number, 20 divided by 2 equals 10, and in this case 40 divided by 2 is 20. So this is the acceleration. So the acceleration of the object on the right is greater. So this is just illustrating the concept of acceleration, right? The rate at which the speed is changing. Saw your hand up. Jenna, is it?
Yes, but she was saying that she thought acceleration was a change in speed. The book says that it's a change in speed and direction.
Correct. Yes. So in what I have extra credit to you for bringing that up, right? Now, speed is a magnitude. It's just a number, right? If I'm traveling 30 miles per hour, the speed is equal to 30 miles per hour. Velocity equals, that's v. Velocity equals speed plus direction. So if I were to say 30 miles per hour due east, that is now a velocity. Acceleration is the change of rate of speed, that's the magnitude, plus the direction. So you're right that it does include direction as well. So I'll have to say, in what direction am I accelerating? If I'm driving north, and if I press hard on the gas, I'm accelerating due north. If I put on the brakes, what happens is I am decelerating, or conversely, I am accelerating due south, because I'm slowing the car down. Right? Cool? Yes, sir?
So if you have something falling freely through the air, isn't it eventually going to reach a terminal velocity and just stop going faster?
Correct. Beyond the scope of this particular lecture, but I'll comment on that. Right? And you're right. Proceed with your question.
If that does happen and it stops accelerating, correct?
Mm-hmm.
So with that, you said basically A was correct, but looking at it deeper, C is correct. If it eventually stops accelerating, though, wouldn't that just make A correct? I'm just trying to get it straight in my head. I'm not trying to...
No, not a problem. Okay. I think... I'm sorry?
It's still accelerated at some point.
Yes. Why? That's a good point. This is beautiful. The questions that you're bringing up, that totally awesome. It shows me that you're thinking about the concepts, which is exactly what I want, right? I want you to do. And this also illustrates the fact that knowledge in general is like an onion. Science is like an onion. Physics is like an onion, right? Lots of tears involved. Okay, that's a joke, right? So, think of an onion, right? When you're first introduced to a topic, you get a superficial level of understanding of the object. So you're looking at the first level of the onion. Now you peel off that skin, and what happens is you're at the next level. So your first introductory course will be at the most superficial level. You're looking at the skin of the topic. You take the next level course, you'll be going one level deeper, then the next level, right? You could make an entire lifetime of studying physics or any topic of knowledge. So the things that you guys are bringing up, what you're doing is, by asking these questions, you're drilling down to deeper levels, right? So in illustrating this, we talked about the fact that at the most superficial level, the velocity is increasing due to acceleration, and we said the acceleration is a constant g, the acceleration due to gravity, which means that the acceleration is not increasing. If we go to the next level of knowledge, we then say that the acceleration is increasing because we're getting closer to the Earth, right? The force is getting stronger. The third level of knowledge on the same topic, the same question, is what you brought in, air resistance, beyond the scope of this lecture, but the air resistance is proportional to the velocity. And if I recall, it could be the velocity squared, right? So as the object travels faster and faster, the air resistance goes up at a rate that's greater than the rate at which the force due to gravity is increasing. So the two of those cancel each other. And at some stage, what happens is the air resistance exactly cancels the gravitational attraction. So the object stops accelerating. Now, students will sometimes say, as a result, the velocity is zero, which is incorrect. The object will still be traveling towards the Earth at the velocity that it had gained up to that point, but past that point, the velocity will not increase, right?
Okay.
Again, so that's the third level of understanding, right? The fourth level of understanding would be then to go and look at those things and say, how does the air resistance change versus the change in the acceleration due to gravity, and that will have some kind of an equilibrium. You may find that the velocity gradually drifts upwards or something of that sort, right? Excellent point, extra credit. Yes, sir?
I was just going to say basically the same thing you said, that the velocity and the acceleration would both stop increasing at the same time. There would still be velocity, there would not be acceleration, but neither of them would be increasing.
Yes, once you hit terminal velocity, right?
Yes.
At least that's for the third level of understanding that we talked about. If we go to the fourth level, then we may find that the terminal velocity has a slight drift in one direction or the other, right? And so you can see, so for the level of this course, go with the simplest level of understanding, because this is a conceptual physics, an introductory physics. So if you were to typically answer just the velocity increases and not the acceleration, that's the answer that is at this level of understanding. If you want to say that, okay, I'm aware of multiple levels of understanding, so the answer is this if I consider this, if it's that, if I don't consider this, I'll accept that, right? Okay, because remember that in a class like this, I'm teaching students with a wide range of backgrounds. There's some students who are like totally freaked out by algebra of any kind and may have had no physics, or they may have taken physics like 15 years ago and like are freaked out just coming back to college for the first time, right? And on the other hand, some of you may be total physics whizzes. It may be your passion, and so you may know all this stuff, which is completely cool. So I walk a line, right? between boring to death those who by just repeating stuff that you all know, versus going like, I mean, you have to figure out where the students are, so you're not flying way over their heads or way beneath, right? So that the feedback that I get from you in terms of questions and thinking is what is used, and what I use to get that. The next thing is, it's a lot of times I get the gauge of where the class is based on the students who speak up, right? If it turns out that you are not speaking up, then I don't have a way of gauging where you are. So feel free to stick your hand up and say, hey, could you repeat that? And I'll give you an extra credit, or just explain this, I'll give you an extra credit and go over it. Or if you are shy about speaking up in class, catch me later, right? And say, here's a concept that I'm struggling with, and I'll be happy to talk about it with you during the lab. Okay? Okay, let's look at the next question. A sheet of paper can be withdrawn from under a container of milk without toppling it if the paper is jerked quickly. So here's a container, like a glass of milk, paper on top. Or rather, the paper is beneath and the milk is on top. You yank this quickly, and what happens is the container of milk stays on the table rather than coming with the paper. What is this demonstrating? Okay, show of hands for A. Show of hands for B. Okay, show of hands for C. Show of hands for D. And for E. Okay, so the majority of you went with B, which is the best answer. B for best, right? Now, A. How about A? Is A true or not? A is a true it's a true statement, but it's not the best answer, because A is just a restatement of the fact that the object is not moving. You basically looked at the question and you've given me the same information again. You haven't provided me an explanation, right? It's like saying to me, I ask you, why is this? Thank you. Why is this agua fria not moving? Right? That's my accent of my French. Right? What's the word? Botella? What's the word? Botella?
De agua.
Botella de agua. Okay. So, the botella de agua, why is it not moving? I ask you the question, and you tell me because it's not moving. Okay, let's go to this bottle. Why is this bottle of water not moving? And you tell me, because it's not moving. I already told you. Have you answered the question? You have not, right? Or you may reword the question and give it back to me. So this is an example of that. If the milk carton is not moving, obviously it doesn't have any acceleration. So it's like a statement of the obvious. The question is, why does it have no acceleration? It's because of the inertia of the milk carton, right? It stays stationary because it was stationary to begin with, and inertia is a capturing of that. With that, let me just go ahead and switch this off and make a couple of more